Alright, today on the bench we have not one but two HP 59501B isolated DAC power supply programmer. And these are little HPIB contraptions from the early 70s that are really super easy to set up, and you send them a number and it outputs a voltage that's proportional to your number. I use them right now to drive the graphics recorder to record my clock signal from the atomic clock. Hello and welcome back. As you'll soon see, I will be embarking on a campaign of metrology with HP atomic clocks, with the ultimate goal of taking one clock up a high mountain and measure relativistic time speed up due to the lesser gravity, an effect predicted by Einstein's general theory of relativity. But before I can prove for myself that time is indeed relative, I need to check if my clocks stay in close agreement with each other when next to each other in the lab. In order to do that, I could just gather long-term drift data, we are talking several days, using my trusty HP 5334B universal counter. It should give me a resolution of 100 picoseconds. I'd gather the data points via HPIB on a modern computer, then plot the results on an Excel chart. But that would be both awfully ugly and no fun at all. Instead, let's use our HP 7132A chart recorder to draw the plot in real time. Now that's more like it. I have a rolling plot that I can check at a glance when I walk past the experiment and easily spot the short-term stability and long-term trends. However, the chart recorder is an analog instrument and the counter is digital. So we need some kind of digital to analog conversion to drive the recorder. And that's where our little HP 59501B box comes in. It's part of the HP 59000 series of handy-dandy boxes meant to support nascent digital automation via HPIB, introduced in 1978. So the 59000 series of HPIB boxes appears in 1978, the age of digital automation, and I have almost a whole collection here. Look at that. There is the DAC, or power supply programmer, that we're going to work on. The relay actuators, two of them, so those are really convenient. You can either program them or push the buttons. The timing generator, which we're going to use to measure the clocks. The A to D converter, and the ASCII to parallel converter, which is actually a digital output box. And then also part of the same series are those cute ones over here. There is the extra cute bubble LED 59309A digital clock with an input at 5 MHz for that can take in the atomic clock. So I could make this one atomic. It's a real-time clock. You can interrogate it by HPIB. And then they are the rare but also beautiful Panaplex displays here, the 59304A numeric displays with their neon Panaplex displays. This one is unsuccessfully trying to say boobs, but this one does shell oil correctly. So nice collection of instruments, and those are also forever instruments. There are mention of some of these in the 1999 catalog. But back to the D2A we have today, the HP 59501B, the 1985 revision, which is identical in spec to the A as far as I can tell. It is called an isolated DAC/power supply programmer, as it can also be used to transform most of the HP analog power supplies of the time into digitally controlled ones, although we won't use that capability today. So I have one that I know I need to, there's something wrong with it, I can't zero it. And the other one I just bought on eBay and I just plugged it in, and the part that it had a broken top, which I repaired with some glue, it's functioning very well. By the way, it's a very simple unit. There is no on-off button. You have some adjustments for the zero, the scale of your D2A, and then there's some more adjustments if you can use them to drive a power supply. it basically, you can wire it up so it replaces the zener or the reference in your power supply. At the back, there's just HPIB, the address of the HPIB. This is a good button. You can turn it into bipolar or unipolar. So it can go plus minus. And then there's the output and other things that are to connect to several of the HP power supplies. So that was at the time in the early 70s when the power supplies weren't digital, but this would turn them into digital power supplies. Last but not least, I got the manual, which I have scanned already, put on the web. I'm going to try it. We need something that speaks HPIB, like my HP 9216. And you do output. This one is address 0, so 700, 7 being the HPIB interface and 00 being the address of the instrument. And then you give it a number from 1000 to 1099, or 2000 to 2099. Let's start with 2000. The first number 1 or 2 makes the scale either 1 volt full scale, I think, or 10 volt full scale. So 2999 is supposed to give us 9.98 volts or something like that. Execute. Ooh, the guy missed it. It just went to 9.99. Oh, by the way, here's the HP 3438 we just repaired. We can see it, and then you have the 6-digit one, which you can't see or can't see as nicely. And I'm going to set it back to 2000, which would be 0. Oh, and the 0 is very good. It's in the microvolts, which is the problem in the other supply. It doesn't work at all. And then if I do 2500, it should be at 5 volts. It's at 4997. Oh, let me demonstrate bipolar. I just pressed the same. Then let's try the upper scale on bipolar. Should give me 10 volts. It's off. Okay, so I have a slight adjustment to do here. 0 is going to be off 2 at 200 millivolts. It is. And then if I go negative, it's going to be offset the same. 0. And yeah, that should be minus 10 volts, and it's offset by the same 200 millivolts. Okay. Let me look on my instructions and see how I should do the calibration. Alright, so it told me to hook myself up to the outputs at the back and to send it 2 commands in succession, 1000 and 2000, which will switch between the 2 ranges and put it at 0, and that's what I have done here. So you have this very impressive program. So it sets the address, sends it to 1000, sends it to 2000, and goes back in the loop. And if you could focus, it would be better. Here we go. And I suppose it's going to show us some steps on the scope, and if they are not aligned, the 0 is going to move between the 2. So if we run this, yeah, I got it, and I have little spikes. I suppose that's when it adjusts the. It goes from one to the other, the low range and high range. Okay, I can see a little difference between the 2. And it's a bit noisy, so let's go into. Let's do first high resolution here. Yep. Okay, I think here would be right there, and then I can go into averaging, and it looks nice and flat. Okay, next step is for the 0 in unipolar mode. After I did this interesting initial 0 balance adjustment, I went on to calibrate the min and the max voltage in unipolar mode, and the unit exceeded spec by more than a factor of 10, with the 0 coming in below 0.1 millivolts and the max scale, supposedly 0.999 volts, coming in at 0.99900 volts. It was then time to do the same for the bipolar mode, and that's when things started to go sideways. Then switch on here the units to bipolar, and now we have to send it 1500 and 2500, which is the 0 on bipolar. Enter, and I will run it. And aha! That was fairly far off, which is why my 0 wasn't good. Oops. I cannot get it far enough. That's the same problem I have on the other unit. So here's my problem, I cannot bring it to 0. What could cause that? So I know that the other unit is a big problem. I cannot bring it anywhere close to 0. Okay, let me look at the schematics here. And looking at the schematics, there is not much that can go wrong. We're adjusting the 0 balance here, bipolar 0 balance with this resistor. So I better check that the plus 15 and the minus 15 are actually what we think they should be. And then it goes straight to this op amp, current to voltage converter. So it's an op amp with a gain of, I suppose, 1 or 10. They adjust it depending on the bipolar or monopolar range. So this guy drifting. Oh, I found what it is. It's the switch. Yeah, that's my problem. See, I just twiddle the switch a little bit and it goes from balance to not balance at all, which makes sense, right? If you look at the schematic, the switch is straight into the feedback path of the DC amplifier. I bet you that's what my second unit is suffering from too, that switch. And since this is a well-designed electronics appreciation channel, let's fire up the elevator music and take a look-see at the schematics. Almost 2/3 of it is dedicated to decoding the HPIB bus commands. Surprisingly, this is done with basic TTL logic, no microprocessor or specialized HPIB controller chip inside. Here is the digital to analog converter proper. It is an HP proprietary chip. There are no details about what's inside, but I have a guess. I bet you it's another one of these hybrid chips with lots of high precision resistors switched in and out by FET transistors, as we had seen on the HP 3438 DVM. The doc says that the chip converts the BCD coded digital inputs, that is, the 3 digits from 0 to 999 that we sent it, into a current from 0 to 2.5 milliamps. It is followed by a current to voltage converter, which is just a giant op amp. The HPIB decoding is such a good example of TTL logic that I thought I'd give you a tour of it. Feel free to skip the logic explanation as there are no faults in this section. It helps that the decoder only needs to recognize 2 HPIB commands, listen and unlisten, and to latch in 4 ASCII digits sent in a row. A listen command is the combination of the attention line, which signals that what is on the HPIB bus should be interpreted as a command rather than data, and the proper values of data bits 6 and 7. You can see how this combo is detected by gate U6. But we only want to listen if our HPIB address is included in the command. The HPIB address is sent along on the 5 lower data bits. You can see how they are decoded and compared to the address set switches at the back of the instrument by U3. If we have both a listen command match and an address match, then gate U9 turns on and sets the flip-flop U12 to the listen state. The instrument has now recognized that the HPIB controller wants to talk to it and is about to send us 4 data bytes. The green LED that says listen on the front panel will turn on, and the listen signal will open the gate to the clock generator. There is a bit of noodle logic at the bottom that handles the 3-wire handshake protocol. It might be slightly noodly, but what it does is fairly simple. It generates an acquired data signal pulse, called ACDS, when it's time for us to look at the stuff on the bus. So now that we are listening, and if the next byte is data and not a command, which we can tell from the ATN line, at the time we get the ACDS signal, the clock generator will generate a pulse, simply called clock here. Since we are supposed to get 4 data bytes, we will get 4 clock pulses, 1 for each digit sent to us. The clock then goes through U15, an opto-isolator, and so do the 4 lower data bits. This is what isolates the ground of the HPIB controller from the ground of our DAC output, and why this is called an isolated DAC. Our 4 clock pulses, 1 for each data byte, then go to the data storage sequencer. That's a big name for something that simply counts up to 4. Oh yeah. The next time my 3-year-old nephew manages to count up to 4, I'll bestow him with the title of Data Storage Sequencer. This prodigious circuit is implemented with a shift register that shifts a single bit around, so its 4 outputs turn on in sequence, one at a time. They'll each enable a latch chip where our data byte will get memorized. The first data byte gets latched into a simple flip-flop, which only cares about bits 0 and 1. That's because all it has to do is decide if the first number is a 1 or a 2 in order to choose the low or the high range. The next digits should be ASCII 0 to 9, so we care only about the 4 lower bits. These 4 bits are latched in succession on chips U18, U19 and U20 as directed by our toddler logic, aka the sequencer. Our toddler logic is also arranged so that right after the 4th count, it resets itself while emitting a 5th pulse, the load pulse. This goes to a second set of latches identical to the first ones. So the 4 digits that had been accumulated in the first column of latches are now transferred all at once to the second column of latches. That column used to contain the old DAC value and is now cleanly updated all at once. And voila, our DAC is now updated with the new value, and the analog signal comes out of DAC out on pin 9. Yay! HPIB message decoded. There is one more thing that the HPIB logic needs to do, which is recognizing the unlisten command. Unlisten is a combo of attention and some specific combo of data bits 1 to 7. You can see how these bits are combined into the large gate U4. If we get a match, we have an unlisten command and the listen flip-flop is reset. Add 2 reset lines, one coming from power on and one coming from IFC, the interface clear signal, and you have a simple HPIB bus decoder made with a few TTL chips. And all that seems to be working perfectly. But trouble awaits after our DAC current gets out of pin 9. The DAC is working in tandem with an external op-amp, which is wired as a transimpedance amplifier. That's another big name to say that it transforms current into voltage. That is simply done by shoving the current straight into the minus pin of the op-amp without the traditional input resistor. Note that we don't see the other traditional feedback resistor, the one that controls the op-amp gain. That's because this precision resistor is hidden inside the DAC chip. Actually, it must be at least 2 resistors, one for the unipolar range and another one for the bipolar range that doubles the gain, since the bipolar operation has twice the voltage span. You can indeed see one pin labeled 10 volts span and another one labeled 20 volts span. This all checks out so far. But what's the matter with our switch S2? That's the unipolar bipolar switch that I think is causing us trouble. It seems to do 2 things. First, it switches in a bipolar reference offset voltage into the DAC, derived from the voltage reference that is also inside the DAC. Undoubtedly, that's to change the DAC midpoint to 0. It also switches in an additional offset adjustment for our transimpedance op amp, so you can fine adjust the 0 volt in addition to the two endpoints. And that's the adjustment that we can't get right. At first, I thought that the offset adjustment was not working because of the switch. But the switch has a huge 121 kilo ohm resistor in series, so a little bit of extra resistance in the switch will not do any harm. Instead, I believe that the added switch resistance in the reference voltage circuit throws off the DAC midpoint and makes it impossible to correct it within the range of the 0 adjustment. I think we have found the root cause of our problem. The rest of the circuit is a traditional voltage amplifier. Nothing super special except maybe for the range switching. I'll skip over it, but the HP manual describes it in detail if you are interested. However, I want to mention the unusual turn-off turn-on control circuit. It's there to make sure that the output of the instrument is 0 at power on and goes back to 0 just before power off. This is essential since this could be controlling a power supply and you don't want to output a large voltage spike. It's a trick circuit with 3 FET analog switches, Q7, Q8 and Q9, that shunt the output amplifier to ground at not just one, but 3 places. They really wanted to make sure there was no output. It takes advantage of the fact that the minus 15 volts comes on and turns off faster than the other supplies. It also uses the second shift register, conveniently left over from U25, to release the shorts only after the first load command is completed. That's it, sorry for the lengthy explanation. There is just a lot happening even in a simple HP instrument like this one. And I kid you not, the spectacular HP service manual explains most of this, if not more. Anyhow, thanks to the superb HP manual, we have a good hunch of what may have gone wrong, probably the switch. Let's repair it. So if there is some bad contact over here, it's not perfect, it's going to put me all over the place, which is exactly what it's doing here. So I need to clean the switch. And I think I have to desolder it. Yeah, got it. Alright. Oh, it's from the front. Okay, I might not have had to take it apart so much. Okay. It's a press construction where the plastic has been, there's like little plastic posts and they've been thermocompressed, so I don't know that we can take it apart easily. I'm going to have a look under the microscope.
Moments later.
Alright, so under the microscope I was able to cut the top of the thermocompressed little post very cleanly with an X-Acto knife, and then you take those two things out, you take the spring out, and it comes apart. And you can see how the thing works. If I can remount it, let's mount it without the spring. It goes in there, it goes like this. So there's not much wipe in there, so if a film of something deposits, it's not going to be a good contact. But I can just wipe it with a cotton swab. Alright, spring, device in, compress the spring, and I do have to glue it back together, dang it. So there's a post here, post there, a post there, and a post there. Alright, indicated, not indicated, alright. And it's 0.32 now, over here. 0.36 over here. 0.33 over here. And 0.33 over here. So I think I am good. Alright, so that's the issue with analog instruments where the switch is in the analog path. That is not ideal when the switch ages. So if I go now to bipolar and I go into my program, there you go. But now I can zero it. Alright, and then I get out of it, and I get back in, I get out of it, and I get back in, and now it's stable. Okay, let's do the alignment procedure once again. Unipolar 0 at the full scale, 0.0 something millivolts, okay. So we set it a 299, 9.990. And I think that's hard to adjust any better than this. So now we are perfect on the non-bipolar mode, and we switch to bipolar. Run. Ah, yeah, and we didn't move a bit. Look, we are still aligned on our 0, so that's working now. It was just a silly switch. Okay. Bipolar is adjusted differently. You adjust the negative endpoint. So I'm going to be at -10 plus 1 millivolt. No, it's not in spec. Okay, -10. And the other end of the spec, and there top end is 9.98 because you have lost 1 bit of resolution. With my hard to turn pot, I don't like this pot. There you go, 998. But it's going to change when I do the other end. Anyway, it's 10.003. Okay, so we are totally within spec, right? The spec is here, and we are one more 0. So I am at -10,000 on one side. I should be at 9.98 on the other side. I'm 9.98001. And now if I try the middle, it should be close to 0, hopefully. Actually, the middle is more important to me. Yeah, it's 400 microvolts. Okay. -5 volts. Yep. -5,006. Plus 5 volts. Yeah, 5.00001. Alright. I am very excellently calibrated. So this handy dandy unit had become inaccurate because of a dirty switch. But once repaired, it's back to the old HP goodness, exceeding its spec by a factor of 10 after 40 years. No Chinese instrument, this one. So in the atomic clock metrology setup it goes, and it's time to look at the other problematic unit, which I bet you has the exact same fault. And this is the second unit that has a similar problem. I can already tell, right? I moved the switch and my 0 is all over the place. Yeah, it's never twice the same thing. Yeah. Look at that. Yeah. Okay. So same issue, I need to do the same contact cleaning and realign it, and probably it will work just as well.
Moments later.
And sure enough, now if I go to the minimum, should be -10. It's minus 10 with 4 zeros in the decimals. Maximum should be 9.98 volts, and it's 9.98000. That should be the zero, which I could never achieve before. And now it's 180 microvolts. So it took me like a quarter of the time as the first one. So that's the beauty. Once you know what it is, it really goes fast. And hopefully that's why I shoot these videos. If you have, well, first because the hardware is beautiful, we always learn something. But if you have the same instrument, and if you happen to, you probably have the same problem, so it'll go way faster. Anyhow, now I have 2 units at work, and I'll see you in the next episode. Whoa, don't go away quite yet. I couldn't resist. I said I wouldn't do it, but I really had to try it. And I know at the beginning of the video I said I wouldn't do it, but I'm going to do it anyhow. Try to control a power supply with the power supply programmer, as they call it, because that's what it's one of its main applications. And the documentation is a little bit hard to read about that. There's a million ways to connect all the power supplies, this way, that way, that way, that way, which is the way I'm using. That way, 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 and that way, to do all kind of stuff. You can control current, voltage, etc. But it turns out that it is a whole bunch of power suppliers supported, and I see most of the ones I have that are not HPID can be supported. This one is no exception. That's the 6226B, and what you have to do is wire them up. In this case it's only 3 wires. Some of the ties have to be removed, you have to add some other one. It's quite complicated, but I think I figured it out. So we'll see if we will have gain control of our power supply via a computer. Okay, so I've never tried it. We'll see if this works. Well, it looks like it's slightly negative. I don't know what that means. I'm just outputting to address 6 this 1000, which should be the 0 on the low range, and this should light up if it receives it, and it did. Let's put it mid-range, 1500, and that didn't do diddly. On this range, no, it's negative. Let's go to 1 volt. It did something. Okay. Oh, because I'm in the wrong mode. I was in bipolar mode. Alright, so that's why it was negative before. 0, 0, 0. Exact. There we go. Now we're at 0. We're not negative anymore. 100. Yeah! 500. Yee-hee! Here we go. And then you have to adjust the full range. So how do I do that? 2999. Exact. Whoop. That's a little too much. Yeah, there you go. Alright, so now I am matched. And that should program it to 10 volts. It did! So let me write a little program here that shows that I have control over this.
Soon after.
Alright, I have come up with this masterpiece of software engineering, which are 2 for loops in BASIC. So for I equals 0 to 15 step of 10, I just scale it up by the right amount and send the result to the DAC. There's a little thing I have to do because it doesn't go to 1000, it just goes to 999. And then, so it go 10, 20, 30, 40, 50 volts. And on the way down, I go down in step of -1 volts. And we run that, and we should go up and down on our supply. And just to To see how precise that is, I put our digital meter. So we'll run 10, 20, 30, 40, 50, 49, 48, 47, 46. So it's remarkably precise for going from digital to analog, then driving the power supply, then back to digital. And we're falling back right on our feet here. See? Good old analog stuff from the 1980s or 70s for the power supply. At least 60s. It's still good after 50 years. 3, 2, 1, 0. Here we go.